All right, today's we're going to be going in section 7.3. So our objectives are the student will be able to write equivalent forms for exponential and logarithmic functions, and write and evaluate and graph logarithmic functions. So we're going to get into the actual working with logarithms that we've talked about so far. So, a logarithm. A logarithm is an exponent to which a specified base is raised to a given value. Logarithms and exponents are inverse operations of each other. So, as we look at this, you're going to see how inverses of exponents are logarithms. And we've done the exponents so far, we haven't done logarithms. All right, so when we look at exponential equations, we've had that before. Remember, the variable is in the exponent, that makes it exponential. So b of x equals a. And the logarithmic equation for that is log, this is said to read base b of a equals x. B for both of these is b is greater than 0 and b is not equal to 1. But b is the base, a is the answer, and x is the exponent. So when you look here, our b is the base from the exponential form, our a is the answer from the exponential form, and the x is the exponent from the exponential form. And we can transfer these back and forth. So, 2 to the 6th equals 64. If I'm going to transform that from exponential to logarithmic form, you can see we're going from here to here. So it would be log, our base is 2, our answer is 64, equals our exponent 6. If we did 4 to the 1st, which is equal to 4, that would be log base 4 of our answer, 4, equals our exponent 1. 5 to the 0 power, anything to the 0 power is 1, but if I do it in logarithmic form, it would be log base 5, my answer is 1, my exponent is 0. And 5 to the negative 2nd, which would be 0.04, would be again log base 5, my answer is 0.04, and the exponent is negative 2. Now if we go back, and we change, so this was all exponential to logarithmic form. Now we're going to go logarithmic form and change it to exponential form. So now my base is 10, my exponent is 2, and my answer is 100. My base is 7, again my exponent is 2, and my answer is 49. Base 8, exponent, negative 1. So if I did this, we know an exponent that would be 1/8 power, which is the fraction 1/8, so that would be 0.125. And 12 to the 0 power, and anything to the 0 power is 1. So a lot of the assignment is just going to be converting from exponential form to logarithmic form, or from logarithmic form to exponential form. Now, it's really important that we understand, and to ask yourself every time where the variable is. Okay? Is the variable in the exponent? Because if it's in the exponent, then I need to convert it to logarithmic form to solve the problem. If the variable is not in the exponent, then we can, like if it's over here, if it's not in the exponent, if it's over here, like let's say it was log 7x equals 3, we want to switch to exponential form because I don't need logarithmic forms except when the variable is in the exponent. So it's really important to ask yourself where the variable is, because that'll tell you where to convert it. If the variable is in the exponent, we need to use logarithms. If it's not, we want the equation in exponential form to solve it. So a couple special properties of logarithms. Logarithms of base b. Okay? If the base is the same as the answer, then our exponent is 1. which if you think about it, if we convert this, our base, if I put it in exponential form, base, exponent, answer, anything to the first power is itself. So it kind of makes sense. But if these are the same, then it's just whatever it's always going to equal 1. If this base and this are the same number. So if I have log 7, 7, I know that that's equal to 1. Or if I have log 12 of 12, I know the answer to that will always be 1. Now, if I have logarithm base b of 1, that's always going to be 0. Because again, if you put it in exponential form, base, exponent, answer. And we know that anything to the 0 power is 1. So it makes it pretty easy that I know if I have log 17 of 1, I know the answer is going to be 0. So anytime the base, if this is 1, then we know it's going to be equal 0. Now, common logarithm is base 10. Okay? So if it's log base 10, that's a common logarithm. And you use that a lot in scientific notation because it's to the 10th power, or 10 to the whatever power you need. So the key on this is we can do base 10 on the calculator. The only thing is, because it's a common log, we won't put a base. So if there's ever no base written on your logarithm, you can assume it's base 10. So log base 10 of 1,000 can be written log 1,000, which we can do on the calculator. If I wanted, I can just go to the calculator and clear that, and do log. So I hit the log button and then enter the number. So I can just do base 10 on the calculator, and it's 3. All right? So, base 10, we just don't need to put a base down. So most of your assignment is going to be with what we call mental math. And so we're going to take mental math problems and we're going to evaluate them mentally. And so some examples. Now there's going to be other ways we can do this later, but for right now on this assignment we're just going to try and do these by setting up so we can do them in our head without having to use any logarithms. So log, remember this is base 10 since there's no base given. And so we want to find out what that equals. So what we're going to do is change it to exponential form. So our base is 10, our exponent is x, and that equals 1,000. And so now what we want to do is try and write these with the same base. So I'm going to change 1,000 into 10 to the third power. And so now we know that this is equal to 3. Because if the bases are the same, the only way they can be equal is if the exponents are the same. So on all of this, what we're going to try and do from now on in these problems is try and write these with the same base. So let's take this one. This would become, the base is 4. Again, this is my exponent, so 4 to the x equals 1/4. And so now we ask ourselves, how can I write 1/4 in base 4? So I'm going to change that to 4 to the negative first power. Because remember, a negative in the exponent means the reciprocal of this. So that would be the same as 1/4. And so now the bases are the same. So x has to equal -1. So I know that log base 4 of 1/4 is equal to -1. Next one. So our base is 10. Again, we don't know our exponent. So this is tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. So I can write that as 10x to x, excuse me, to the 1 over tenths, hundredths, thousandths, 100,000. So that would be 10 to the negative fifth. So let's just go up here. X, 10 to the x equals 10 to the negative fifth power. And so this equals negative 5. Again, once I have the basis the same, the exponents have to be equal. This one, so it's 25 to the x equals 0.04. Well, 0.04 would be 4/100ths, which I can write as 1/25. And so 25x equals 1/25 can be written as 25 to the negative first power. Therefore, x has to equal -1. And so this equals -1. So again, get the bases the same, then the powers have to be the same if they're equal. Let's try a few more. So we go 7 to the x equals 343. So this has to be base 7, and that's to the third power. And so this bases are the same, so x equals 3. Again, 3 to the x equals 1/9. I can write that as 3 to the negative second power. So that equals -2. 0.5 to the x equals 0.25. So again, the difficult thing on this is just finding out how can I write this in the same base. So how can I write 0.25 as 0.5? So that would be to the second power. So that equals 2. And the last one, 1.2 to the x equals 1.44. Again, write this as base 1.2. That would be to the second power. And so that equals 2. So it makes it fairly simple to do these. The only thing on the assignment is make sure that the base here is the same as the base here. So you just have to convert it so they're the same base. And then set the exponents equal to each other and you have your answer. So, exponential form and logarithms are inverse operations, so they cancel each other out. So remember when we talked about inverses before, if I plug an inverse in, it should cancel the other one out. So if I put in this into here, so let's put this in for x, I would get log 3, and now I'm plugging in 3 to the x. Well, what do our rules say? If these are the same, it's whatever the exponent is, so we get x. So those are inverse operations of each other. Now I want to go over some examples in the book. So we're going to go through, if you look at page 507, example number 4. You're going to have some problems on the assignment like this. It's not very hard. They give you the function. It says f of x equals 3 to the x power, and then they give you some values to plug in. So you plug them in. 3 to the negative second power would be 1/9. 3 to the negative first power, 1/3. Anything to the 0 power is 1. 3 to the first power, 3. 3 to the second power, 9. And we can graph that. That's in the blue. Okay? Remember inverse functions. We just switch the x and the y values. So our x values become our functional values, our y values, and our y values become our x values, and it gives us the red line, which again we talked about is the reflection over that line y equals x. They're also going to have you talk about domain of these, and you have to be careful with the domain. Remember, the domain, I can put anything in for x, so the domain in this case is all real numbers. But the range of this, remember it's going up forever, but it never gets to this x-axis. So our range is y is greater than or equal to 0 because it's everything above that. Well, when you do the inverse, it just switches. So our domain, which was all real numbers, becomes our range. And our range, which was x was greater than 0, becomes our domain. And so our domain is x is greater than 0. So it's really pretty easy. You just plug in the numbers, make your chart, flip your x and y, and just remember your domain and range will also just be switch with each other. The last thing I want to look at is number 5. Because this is one you're going to actually use on the calculator. So it says, chemists regularly test rain samples to determine the rain's acidity or concentration of hydrogen ions, which is H positive. Acidity is measured in pH as given by the function P of H equals a negative log of H positive, where H positive represents the hydrogen ion concentration in moles per liter. So it says find the pH of rainwater from each location. So they've listed it here. They've got it on the chart with those R. And so you can see it says find central New Jersey. Well, if I go to central New Jersey, it's 0.0000316. And so all I do is I plug it in, and this is where we're going to use the graphing calculator, which I'll have to call up. So that equation was negative log 0.000036. So I just use my calculator. Negative log. Remember, we don't put a base, it's base 10, so 0.000036. Enter, and its pH would be 4.444. So you just plug it into the calculator on the problems of that type, and you find the logarithm that way. So, your assignment, page 509, 17 to 33 all, skip number 32. Again, you don't have to make the graphs, just write the charts. If it asks for the inverse, you can just fill out the chart and write the inverse chart. So, good luck on that.